This question states, if an element has sigma x equals 100 megapascals, sigma y equals minus 100 megapascals, and tau xy equals 0 megapascals, what is the maximum in-plane shear stress, and what is the associated angle of rotation theta s? Before we go into Colab and Python to use a trial and error approach to solving this problem, let's talk about what's happening qualitatively. We begin by drawing the element with an appropriate coordinate system with x to the right, y upward, and we note that sigma x is positive. So we can think about the sigma x as having stresses coming out in the x direction, and we give it 100 megapascals for a value. Vertically, we have that sigma y is equal to minus 100 megapascals. So we can put in a value of 100 megapascals with arrows going inward. We could have drawn these arrows coming outward so that they, on the top would have been in the positive y direction, and in the bottom it would have been in the minus y direction, and then put in a negative 100 megapascals. But this way of expressing things is clearer in terms of what the top and bottom are having acting on them with this negative compressive stress. And tau xy is equal to 0 megapascals, so we won't draw those arrows. If we were to go back and take a look at what we discussed in class, we would find, whoops, I went too far, that when we have a sigma 1 equal to a minus sigma 2, think about it. This is a state of principal stresses. There are no shear stresses present, and the stresses are in opposite directions. This is the case where we have pure shear. So we're going to be interested in orientations that involve a 45-degree transformation from the given state. So it's not a bad idea to go ahead and think about what would an element rotated 45 degrees from the original orientation look like. So we have 45-degree rotation, now x prime coming out this direction, and y prime coming out this direction. 90 degrees, 90 degrees. Now, why have I distorted this element to flatten it like you see here, right? It kind of looks like a squished diamond. I wouldn't expect someone doing this problem for the first time to make all these kinds of realizations using, this kind of thinking or process. Nonetheless, let's think about how an element that's under compression in the vertical direction, in the y direction, and extension or tension in the horizontal x direction would behave. So you could take this element and then impose these arrows on it. And what would you see? You would see that the compressive stress in the y direction is in fact squishing the element. And you would see that the stress in the x direction in tension is in fact elongating the element. And in the x prime y prime reference frame, what would we be able to put on this element to cause this type of distortion? And this distortion does look like shear stress, and we know it's going to be essentially pure shear because of our discussion that we had previously. So if we draw the shear stresses, we kind of see we're going to draw them so that their heads meet up here, and it's kind of pulling, right, this and narrowing it at the same time to the left and also to the right. And we can draw these stresses before we even think about their magnitudes, which is what we're doing now. But if we look at the direction that these stresses end up acting on the x prime face, what we see is that the stress is in the minus y direction. Okay, so this is supposed to be parallel to that. So that means that the tau xy, or I guess I should say, whoops, this is kind of a little boo-boo. This should be tau x prime y prime is going to be less than 0. And now let's go ahead and start to think about what the actual values will be for this transformed state of stress. It's an equivalent state of stress, but we haven't solved for what this tau x prime y prime might be. And we're going to use the trial and error method, so let's go ahead and go back to Python. And from question 1, what you, let's see, where we, oh, that's not it. Oh, that's the answer, huh? Okay. Well, anyway. Question 1 had us looking at principal stresses, and we were calculating max sigma x prime, max sigma y prime, and minimums of those. And then this next problem is for principal stresses, so let's keep going down. And here we go. Maximum in-plane shear stress for a given state of stress. So what we're going to do is we're going to plug in our values and see what we get. So we have sigma x 100 megapascals, sigma y equals minus 100 pascals, and that was the state of principal stress or principal stresses, and the tau xy was equal to 0. So now when we plot this, okay, it's been so long that it's going to throw an error because I need to go back all the way to the top and make sure that I run. Maybe it was, I don't know. I guess let's see, did it throw an error? It looks like it did not throw an error. Okay, so it had kept the libraries in even though I had to reconnect. What do we see here? We see that we have a plot of the sigma x. Let's see, can I move this down? There we go. A plot of the sigma x prime versus the rotation angle, and it starts at 100 megapascals. That's a good sign, and it goes down and up. We have a plot for tau x prime y prime. It starts at 0. That's a good sign. That's what we put in to our problem. And we see that sigma y prime is minus 100 megapascals, and that's a good sign too. That's what we were predicting. So we also see that the sigma, or the tau x prime y prime, it goes negative at 45 degrees, and it looks like it might be maxing or minimizing, however you want to say it. It has it has a negative peak at 45 degrees, about minus 100 megapascals, and we also see that at 45 degrees, sigma y prime looks like it's going to 0, and at 45 degrees, sigma x prime also looks like it's going about to 0. So let's go back to our slide. We're going to copy this one in, or I've already copied it in, and we're going to proceed from there. Okay, we'll see, whoops, that's not the right one. Here we go. So we're going to paste that one in. And we also have additional scripts that help us figure out what's happening or where, and what angle and what are the actual values, even though it seems maybe pretty obvious that it's minus 100 and then it goes to plus 100 at 135 degrees of rotation. Let's go ahead and use the other parts of the script that are available to us. So here, we'll run this. This is going to spit out the max tau xy prime equals something, and it says what that rotation angle is. It's right at 135 degrees. And we'll see that min tau xy prime is equal to minus 100 megapascals and at 45 degrees. when this I copied in to the presentation, and we see that we might be able to explain what we have here quantitatively now. Look, we said it was 45 degrees of rotation that was going to be interesting for the case of pure shear and calculating these maximum or minimum in-plane shear stresses. So at 45 degrees, it's minus 100 megapascals. We predicted that tau x prime y prime would be less than 0, and that is in fact what we do see. So we can say, here, look, this is the 45-degree situation. This is the minimum, or a tau x prime y prime, that's less than 0, and it's at minus 100 megapascals. Now, this other scenario is when we rotate another 90 degrees. Well, what happens when we rotate another 90 degrees? Well, x prime will come over here, and y prime will come out over here. So we could call this y prime now, or we could call this x prime 2 the former y prime, or y prime becoming the x prime 2. And we could call this direction out here y prime 2, which is in the opposite direction as x prime. Now these are not stresses, these are coordinate systems. So their direction and the face they're on does have more significance than, say, sigma x being opposite directions coming out of opposite faces. What do we see here? We see that in this orientation, here is the x prime phase. This is the positive x prime phase, or x prime 2 phase, right here. The green is where my arrow is. And the stress is acting on that face in which direction? The positive y prime 2 phase. And that's great. That means that this depiction of the stress, the tau x prime y prime 2, if we want. So let's go ahead and we can write that out. This would be a tau x prime 2 y prime 2 over here. This is going to be positive, and that's what we see as well, that we have 100 megapascals here corresponding to this value. This, I think, is a typo in the script, so we're going to ignore that. Let me take a look to see why that happened. Okay, so that we're going to ignore. We're looking at these angles that were spit out. Why did this happen? This happened. So at theta, okay, tau x prime. Why? Adds because it must have been for a different problem. It's not the copied and pasted from this. Look at that. Okay, so that's a mistake that I made when I copied and pasted previously. So for the sake of not making that mistake in the future, let's go ahead and we'll X out of this. We'll keep our annotations, and we'll try to come back here, and I'll take this person out and put this there, or try to take some of these out. And this is, you could have stopped the video by now. Not offended. This is not necessarily the best use of time, but you can see my attempts to edit things appropriately. Okay, and there we have it. And I guess I'll add that this was the tau x prime y 2 y prime 2 there on this face. Okay, I hope you found this information useful. Thank you for watching.